Right. So yeah, just as was announced, I work at DayRobot as a machine learning engineer. So I work with automated ML on a daily basis. So many of these topics that I'll be discussing today are very dear to me as a part of my day-to-day job. I teach a little bit AI and machine learning to bachelor and master degree students. Also, when I have free time, I compete on Kaggle sometimes. Right. So. For those of you who have your own laptops and would like to follow the materials of this session, you can clone my repository. You'll find the slides that I'm showing here. You'll also find some Jupyter notebooks that you can run. So it's not mandatory, but if it's more comfortable for you, you can just follow the materials in the repo. All right. So what this whole session is about. So if we were to define target leakage in just a few simple terms, it's when somehow data that will not known to us when we deploy the model somehow sneaks in to our training set. And why is this an issue? So it might not seem like a big problem at the first sight, but if we think about what we care about more, do we care about getting good evaluation scores when we develop the model? Or do we care about good model accuracy when we actually deploy the model? And why this issue is so tricky is that if we have target leakage in our data set and we build a machine learning model that was built on leaked data, we have a very unfortunate situation when we are very confident as a data scientist that our model will perform well when we deploy it into production. But then we deploy it into production, well, because our scores were great. And then we deploy it into production and see that the model is a few times worse than we anticipated it to be. So that's a pretty undesirable thing to have because it can cost losses in business. It can cost even like human health and lives in the unfortunate cases. So we have to be extra careful to have our validation score when we develop the model represent the actual performance of the model on unseen data. And usually when I spoke to people about that, I got a response like this quite often. So, but I always validate my model on unseen data. So I've been doing this for a while. I know that I should not be using training score as a measure of how my model will perform in production. So we know our way around the block. We know that we have to partition our model into validation holdout sets using CVE or and evaluate the model on the data the model has not seen before. But the trick is, it's not about the row indices, whether we train and validate on different row indices and so forth. It's about the individual values in the training data. So the tricky part of target leakage is that you can have certain values sneak into your training set, and they are somehow slightly descriptive of the target or strongly descriptive of the target. It's not always easy to see this. Using automated tools or using just some visual inspection, and that's the danger of this issue and why it's so easy even for an expert to accidentally introduce target leakage. So we're going to go through some examples from more simple and obvious to more complicated and not so obvious. And I have some examples implemented in the code in the repo that you see. So the tricky part is that it's not only about partitioning, it's not only about how you validate your model, whether you're using CV or time series split or TVH or anything else. It's about the fact that target leakage can actually be introduced throughout the entire project lifecycle. So it's not only about partitioning, for example, but you can also introduce target leakage when you collect the data, even before you start feature engineering or feature selection or model training. You can introduce leakage when you do feature engineering. You can introduce leakage when you train and tune your model. You can even introduce some leakage when you evaluate the model you already trained and built. So we're going to go through examples of target leakage on each of these possible steps in the data science project. So I excluded deployment from this because the deployment phase is where we will be reaping the results of target leakage. So it's not much that we can introduce on deployment stage, but what we do before deployment is what matters. So leakage in data collection. A very simple, obvious example just to get warmed up with the problem of target leakage. let's say we want to build a service that helps professional understand what the demand for their skills is on a particular market. So for example, a person wants to move and work in a particular country, and they want to get an estimate of what annual income they can expect. They have certain skills, they have certain background, they have certain work experience, certain titles, certain specialty, and we would like to predict this column, annual income USD. Perhaps many of you have found the leakage already in this data set. So given our earlier definition, what would be a column that we are unlikely to see at prediction time, but is strongly descriptive of the target? So I would say it's this column, monthly salary GBP. So it's quite obvious when we have very few columns on the slide, when we have very little data set, just this toy example. But in practice, you may have very cryptic feature names. You can have thousands of columns in your database, especially occurring as a result of joining multiple sources like relational databases, other sources. It's not always obvious, like column will not be always named the same, but it can be measured in different units and can be measured in different resolutions. So in this case, we have target measured in as annual income in US dollars, but we have an additional column which is monthly salary measured in pounds. So this is the case when the target is actually a function of one of the features, and just because we have multiple copies of the data in our different columns, this column is a leak, because let's imagine the deployment scenario of this model. So a person can enter their data, like what kind of skills they have, what kind of experience they have, and the model is supposed to predict what kind of salary they can expect in this particular market. So they won't be employed at that company, in that market, at the time of prediction. So we will not know their monthly salary. Therefore, our prediction of annual salary based on monthly salary is meaningless in this deployment situation. So a similar example, sometimes we can, like business analysts can generate additional columns for easier reporting, for building dashboards more easily. So in this case, it's a very common use case for telecom companies. So based on the usage patterns of some cell phone services, they would like to predict the demography of their subscribers. So for example, given the usage pattern of particular telecom services, we would like to predict whether it's male or female, or what kind of age group they belong to. And sometimes relational databases, and not even sometimes, but very often, relational databases in organizations are immutable and not snapshotable. So a business analyst might write a SQL query that for already known subscribers can derive this group column, which is male from 18 to 25, female from 40 to 60. And if we just blindly export this data from a relational database and feed it into a machine learning model, it can actually pick up this column very effectively. And of course, it's not a realistically good model for a deployment scenario, because we won't have this derived column at the time of prediction. We will just have a particular subscriber. We will aggregate some information about how many SMS messages they sent, how many megabytes of data they used, how many voice calls they made, or minutes spent in voice calls, and we would like to predict, for example, the gender or the age group. So this group column will be in the future relative to our point of prediction. So it doesn't make sense to deploy a model with these columns. So yeah, this is a very basic scenario, but I've actually seen people do this. So every example I'm going to show today, I've actually seen people do this and make mistakes based on it. So this is something that people sometimes do, especially if we don't have a good data dictionary in place, or we don't understand the meaning of individual columns, or if the columns or values are very cryptic. But a powerful machine learning model that can leverage text, categoricals, numerics at the same time can actually pick up these patterns. Right. This is a more subtle example, but still very similar to our previous two examples. So let's say we have a credit scoring case. So we have details of of a person that applies for a loan. So they have a certain level of education, they have a certain marital status, they have a certain annual income, and why they are applying for a loan, either start their own startup or buy a house, buy a car, get married, go to vacation. And we would like to predict whether this client is trustworthy, whether we can trust this client with repaying the loan in time. Actually, in banking, it's equally bad for the client to repay the loan too late or repay the loan too early. Sometimes early repayment is also an issue in banking. So we would like to predict this target. So we have some historical data set. It's a very common use case. We have a historical data set about this particular client. They ended up repaying the loan. This particular client ended up defaulting on the loan. And we just take a snapshot of this data from the database and train our machine learning model with it. But what's the issue with this data set? So we have this very interesting column, late payment reminders, which actually means how many times the client was already called and reminded about a late payment they need to make. So if we imagine how the workflow is going to look when we deploy this model, so we actually want to deploy a model so that a new client comes through our door, they fill out their details, and we want to make a prediction of the client's trustworthiness at this point, when they just only entered their personal data, their financial status, and so on, but they haven't yet received a loan from our bank. So obviously, when we deploy this model, we won't have this counter of late payment reminders for this client. So this is a very common situation in real life. This normally occurs because of the fact that many relational databases and organizations don't have snapshot ability. So as more facts become available, as we accept this client and start providing them our services, old records get overwritten with new facts. So at the time when the client is new, they will have a new record in the database, and this column will be blank or zero. But when the client already we have facts of late payments and we have to remind them, so database gets overwritten with these new values. So this is the issue with setting up the problem initially, because our data is not snapshotable. It has to be snapshotable to apply machine learning properly. So we have to make sure that the snapshots we take for training and testing our machine learning models actually represent the point in time where we will be actually making predictions in the real life when we deploy this model. So that's why proper snapshotability of data matters a lot, and it's easy to introduce target leakage by overriding previous records with new facts. So it's also very common in healthcare. So for example, we can have a column, so we have to predict whether the patient will have some kind of disease, and the accidental contamination column can contain the fact like, did we already perform surgeries in our hospital for this patient for this particular disease? Or have they already received a prescription for a particular disease? So that's when we get these future and past mixed up. So the fact of so surgery happens after we admit the patient, and prescriptions happen after we admit the patient. So we cannot predict this information early. Right. So let's move on to leakage and feature engineering. So that was the previous two issues where the data is typically mutable or contains information that won't be available to us at prediction time, but there's also occurrences of these facts in feature engineering. So let's look at a standard example. So we can have some models that are mathematically sensitive to feature scale or to outliers like linear models or KNN. So we know that distance matters a lot, scale of the features matters a lot for convergence, for machine precision purposes, and so on. So we know that, often for machine learning, for KNN, you have to scale the features using, for example, standard scalars, so like bring numeric features to zero mean and unit variance. So we apply this standard scalar to our data set from scikit-learn, and we partition our data into train and test and build our models. But actually, there's an issue with this approach. So the issue is that we applied transformation to our data set before allocating the holdout, before we allocated the test set. So what can happen? The result might not be very impactful sometimes, but it still impacts the generalization ability of our model. So we first apply standard scaling, then we partition into train and test, which means if we have an outlier or a bunch of outliers in the test set, but we don't have them in the train set, we actually leak the information about the distribution of the features into the training pipeline. So our standard scaler will fit on the entire data set. So it will remember that there's a certain mean and a certain standard deviation. But what happens is that our standard scaler actually looks at the entire data set. So it will combine the statistics from both the training set and the test set. So we first fit the standard scaler, then we partition. So that way it will capture the information available in test set, and that information should not be available to us when we build the model. This is more, the impact is higher when we actually have time-aware data set. So for example, we have some data set that is influenced by the inflation in the economy, or prices for certain goods and services increasing throughout the time. And if we apply daytime partitioning to our data set, like standard scale first and then apply daytime partitioning, that means we will introduce information about future inflation in the economy into the past where we train the model. So how do we fix this? We fix this in a pretty simple way. So we partition first, then apply any kind of feature transformation pre-processing. So what we are going to do in this particular case was standard scaling. So standard scaling, when it's being fit, it remembers two parameters. What is the mean value of each feature in our training set, and what's the standard deviation? So we have to actually partition the data first into training set, then use standard scaler only on the training set, remember the mean and the variance and the standard deviation that we derived from fitting standard scaler on the training set. And then we just transform the test set. So we don't fit standard scaler on the entire data set. We fit this only on this small training partition, and then use the parameters frozen here to transform our test set. That would give us a more robust estimate into how our model will perform when it starts seeing new data in the real life. So this is not relevant only to standard scaler. Actually, it's relevant to any kind of feature engineering or preprocessing you do. So for example, if you have text, a common mistake I've seen people do is actually, let's say we decided to model our text data using document term matrices, so like TF, IDF, or any kind of bag of words model. So we have to derive this matrix where the columns represent individual words or n-grams that we see in the data set, and rows represent the documents, so the individual records in the database. So what can happen is that people use the entire data set, both training and test combined, to come up with the vocabulary of the model. But actually it can, it also leaks out of vocabulary word into the training subset. So common problem with text models is that the language evolves, new words appear, new terms appear, and it's not uncommon in production for the model to start seeing words that it's not seen before. And in this case, we will actually deprive our models of this fact, because as far as our model training is concerned, we know all the words because we analyzed the entire set before partitioning into train and test. So we actually have to do the same thing here. So we partition first, learn DTM columns only on the training subset, and then transform the test set using our vectorizer. So we fit the vectorizer on the training subset, then transform the test set. So by test set, I mean any evaluation set you have, so either backtesting or CV validation fold or holdout. Same deal with categoricals. So same deal with one-hot encoding of categoricals. So you might not have some of the levels of the categorical variable in the training set, but you can have it in the test set, or you can have some rare new categories appear in the test set that you did not have in the training set. So it's the same deal with categoricals. You should not leak the information. So when we fit categorical encoders on the entire training set, we can accidentally leak the information about the cardinality of the frequency or of a particular categorical level into our training set. So the recipe is identical in this case too. So partition first, then train the encoder on the training part, transform the test part. All right, so when it comes to leakage and partitioning, I would say this is probably the most mistake-rich area for complicated cases. So, and I saw a very interesting example from no other than Andrew Wang. So Andrew Wang published, tweeted a while ago that his group developed a deep learning model that can detect pneumonia and other and some other diseases from chest X-rays using deep learning. And linked the paper, gave all the details. And actually, if we look at the paper, interesting details show up. So they have almost 120 unique images, but only 30,000 unique patients. And they say they randomly partition the data set into 80% training and 20% validation. So we have, and there was a guy who actually picked it up pretty fast and replied, like, aren't you concerned that you have 4 times fewer patients than you have unique images? That means potentially if you apply a random training validation split, you may have patients appearing in both validation set and training set. And that's a big deal because we cannot always say for sure that our deep learning model actually learns to detect pneumonia in chest X-rays. If we have 4 times more unique images than patients, a deep learning model may actually pick up some detail of patient anatomy, like a scar somewhere in the internal organs, or it can learn some particular noise provided by the medical imaging hardware instead of learning to detect the actual disease. So this situation is called group leakage. So we actually have same person potentially appearing in the training set and the validation set. And they actually fixed it. They released new versions of the paper, and they edited this setup section, and they literally fixed it in the newer versions, saying there's no patient overlap between the sets, but the AUC dropped for many diseases. So they actually had more optimistic scores in the original version when they had this group leakage between training and validation set. And for many of those disease categories, AUC scores have actually dropped after they fixed the partitioning. So this is a thing that happens quite a lot. So if you have some data representing particular groups in your data set, you have to apply a specific type of partitioning for this problem, which is called group partitioning. So a common case where you would like to apply this partitioning is when you have the problem of a cold start. So, for example, you work in public health and you would like to predict something like the spread of disease or something like that, or spread of crime as a result of new policing legislation or something like that. And you have data only collected for 3 U.S. states, for example, Illinois, Oklahoma, and Texas. And you would like to predict the state you haven't seen before, like North Carolina in this case. So if we have this cold start problem, we have some groups that we have data on, but we have another prediction group that we don't have any correct answers for. That means we have to set up our validation framework to match this problem that we have. So if we have the problem of predicting a previously unseen state, we have to apply the same partitioning to our machine learning experiment. So, and the way it's done is through group partitioning and out-of-group validation. So if we have a problem of predicting the state we haven't seen before, we don't have supervised labels for the state, that means we have to repeat the same experiment in our training data. So let's imagine we haven't seen Texas, so we train on Illinois and Oklahoma in one fold and validate on Texas. Then we train on Illinois and Texas, validate on Oklahoma, validate on Oklahoma, train on Oklahoma and Texas, validate on Illinois. That's how you typically solve cases like that when you know you'll have to predict groups you haven't seen before. And that's actually what we can do even with Andrew Wang's case. So we can actually assign a group ID to each patient and apply group partitioning to this problem. So like train on a particular bunch of patients, validate on another bunch of patients. Also, a thing that happens pretty often is leakage in oversampling or augmentation. So sometimes maybe the data set is very imbalanced and you would like to oversample the minority class to have a better target balance, or It's very common in image modeling to augment the images in the training set by applying random skews, random rotations, random color filters, random flips. So people would sometimes create copies of individual rows. It can also happen with some machine learning software that expects, for example, a minimum number of rows in the training set. So, for example, if some tool expects like 100 rows in your training set and you only have 50, so a user can sometimes try to just copy the data set and feed it into the tool and apply random partitioning. Or it can also, it's an interesting augmentation technique that I've sometimes used with pairwise data. So if you have something like a similarity prediction problem, one thing that comes to mind is the recent Kaggle competition from Quora, where you have two question titles and you have to predict whether it's a duplicate question, like whether the two question titles mean the same thing. So if you have this pairwise data, you can use the information that it's pairs, and similarity relation should be can be mirrored. So like if A is similar to B, then B is similar to A. So a simple augmentation technique to use in this case and get 100% free additional training data is to flip the pairs and append them to your data set. So if you have A and B, feature describing like question A, question B, you can actually flip them and augment them. But the problem is, where do we do this augmentation or oversampling? So if we use random partitioning, we should not do augmentation or oversampling before we partition the data, because of the same thing as with entry-wang. We can end up, if the random seed is not lucky for us, we can actually get one copy of a training row in the training set and another copy of the row in the validation set. That means we will effectively be evaluating our model on in-sample data, because we already trained on this particular row, and if its copy or augmented version ends up in the validation set, we will effectively be predicting on the data we've trained on. And it's not a reliable estimate of the sample performance. So we just have to flip these two parts. Just as before, we have to partition first, then augment the training data. So I would even say we shouldn't bother with augmenting the test data or oversampling the test data, because we only have to enrich the training set and leave the test set to be an estimate of out-of-sample performance when the target balance is real life. So we just partition first, then go to the training set and augment or oversample it, just to make sure we don't get copies scattered throughout our validation framework. Right, so what if we apply random partitioning, but our data is time series? So we have for example, some popularity of a search term in Google, or growth of demand for some service, like maybe number of downloads for a particular app. So we have a time series forecasting problem. Like we have to predict how many laptops we will sell in our shop the next week. And what if we apply random partitioning to it? I've actually seen people try to do this. So what we end up with is, if we try to randomly partition a time series data set, we also introduce target leakage, because we can have a situation like this, where we have this part in the training set, this part in the training set, and this part in the test set. So it's much more easy for a model, for example, if we have a stock price or popularity of a product, it's much easier for a model to interpolate between the start date and the end date if the start date and the end date was present in the training set. So we should avoid, actually, for any time-aware model, for any time-aware project where date is a sensitive dimension to our data. So when we are impacted with economic factors like inflation, employment, and legislation, and so on, we should make sure to partition our data such that we always train on the past and validate on the future. So the proper way to avoid target leakage from the future into the past would be to partition the data using daytime partitioning and out-of-time validation. So how many of you attended Mike and Mark's workshop on time series feature engineering? Oh, cool. So my two colleagues gave a workshop on time series feature engineering, and they also covered this subject extensively. So we have to make sure that whatever problem we're building a machine learning model for, we have to make sure that our validation framework represents the actual problem we will face when we deploy this model into the wild. So if we, in a time series forecasting problem, what we're trying to solve is how can we learn from historical data to forecast the sequence of events into the future. So our validation setup should represent that exact case. So the way we partition data for time series forecasting, or generally for daytime partitioning, is that we make these steps into the future, or it can be called like forward steps or backtesting. So we train on some data far into the past and validate on a bit of data from the future. So you might not necessarily see the gray and green colors here, but this part is green, this part is green, this part is red. So we train on some data from the past and validate it on a piece of data from the more recent future. Then we extend our data set, we add some more recent data and validate even more recent data. Then we add even more recent data and evaluate on yet more recent data. So if when we deploy a time series forecasting model, we will see some history until now and we will start predicting the future. So this validation setup perfectly represents the model, the problem we have in the real life. So by estimating how the model performs on strictly future data, we have a robust estimate of how our model will perform when we deploy it and it starts seeing future observations. Future stock prices, future demand for goods, and so on. So what can go wrong in the model training and model tuning? So as it turns out, there's also a couple of accidental mistakes we can do there. So one example would be trying to do too many things on the same cross-validation split. So sometimes it's not obvious to think about this problem in this way, but actually, if we do feature selection, it's a process that needs to be validated. If we do model selection, it's also a process that needs to be validated. If we do hyperparameter tuning, it's also a process that needs to be validated. So and by repeating all of this work on the same validation fold, we can slightly overtune the model to individual folds in the data. So it would be more preferable if we have something like hyperparameter tuning, feature selection, model selection, to actually use different splits for each of these. So do feature selection on one cross-validation split with particular fold setup. Do hyperparameter tuning on another k-fold split to not reuse the same validation folds over and over again. So another thing that we can do is also a bit related to cross-validation. So who attended Marius Michaelidis' workshop on StackNet? So one of the Kaggle Grandmaster, former champion of the world, nicknamed Casanova, gave a talk earlier this morning about stacking models. So how many of you are familiar with the model stacking and model ensembling? All right, about 40%. So yeah, I'll probably explain it briefly. So usually the accuracy of the model increases when we build not a single model but build a committee of models. So there can be one model that is good at predicting particular kinds of rows. There can be another model that is good at predicting another kind of rows. So like trees can be good at particular features. Linear models can be good with other types of features or other types of situations. So why not build all of the models and make a committee out of them? So either average their predictions. That would be a simpler example of ensembling. So we build multiple predictive models and we average their predictions. And these average predictions very often help cancel out the individual model errors and provide a more stable prediction. So it's very often that simply training multiple diverse models and averaging their predictions helps to boost the scores a little bit, especially in a competitive environment. So in Kaggle, where every like third, fourth, fifth decimal points matters a lot, we can get quite a lot of boost on averaging predictions alone. So stacking takes this one step further. So instead of just building many diverse models and averaging their predictions, stacking is basically about building a supervisor model, like building a chairman model that will take these predictions from the committee as features and actually learn how to trust each member of the committee. So we have two-level machine learning model now. So we have committee members that for example, one model votes, I say this is a non-trustworthy client, we should not give them the loan. The other model votes, this is a good client. The third model votes, this is a bad client, and so on. And the chairman model, the second level model, actually looks at the predictions of these individual models as features, and it trains on these meta features to pass the final decision. So the chairman only looks at the votes from the committee and learns on the votes to pass the final judgment about whether it's a good model or not. And I've actually seen people do this. So since we say that in model stacking we should use predictions of first level models as features, let's do exactly that. So we train the model on number one, for example, like a gradient boosting machine. We train it on the training set, predict the entire training set, obtain meta features from this model. Then we train something like logistic regression, predict the entire training set, and we have our meta features. So we can train our chairman on these two features and the target to predict. But if we actually do it like this, it's very easy to leak the target on in these meta features. So the more proper way to do stacking would be to collect stack predictions, to do out-of-fold predictions. So the proper way to do this, we have to make sure that these meta features are derived from the data the model haven't seen. So the way we do this, we leverage our well-known k-fold CV partitioning, and we train on the training part and predict the validation part. And we collect this small bit of predictions, only like 1/5 of the prediction we need. So we store it here, then we repeat for another CV fold. So let's say this part ends up our validation fold. So we train on this, predict on this, collect our another building block. And we repeat this process for 5 cross-validation folds, fill out this column, and then we repeat the same process for the second model, and we fill out this column. So that way, our meta features for stacking always come from out-of-sample data. So they are not in-sample predictions, they always come from the predictions on the data the model hasn't seen before. That is, of course, given we haven't introduced any leakage in data collection or feature engineering or partitioning before. So if all our steps down the up the pipeline are good, so if our data collection is good, if our feature engineering is good, if our partitioning is good, then this will provide a robust, like less leakage-free estimates of the meta features. So yeah, that's the way it's done for model stacking. An entirely different, entirely special type of leakage is what you can sometimes find in the competitive machine learning. So do many of you compete on Kaggle or different platforms? Okay. So you. Okay. Yeah, Santander as well. Yeah. In competitive machine learning, it's quite common to face target leakage simply because Kaggle competition can often contain real-world dirty data provided by data scientists from actual companies. So like a bank wants to predict the value of customer transactions, or an insurance company wants to predict losses from claims, or a hospital wants to predict patient readmission. On Kaggle, many real companies provide their data and offer money prizes to the people who can build the best predictive models on their data. And it's actually real-world dirty data from real organizations quite often. And what happens if you release a data set, a real-life dirty data set, to 5,000 of data scientists, you can expect them to steamroll this data set completely. So they will find every little mistake, every little feature, every little detail that they can exploit for better predictions. Because in competitions like Kaggle, most of the time, the only thing that matters is how accurate your evaluation metric is. So most of the competitions don't care about prediction latency, about time it takes to train these models, only about how it performs on the test set and like what the metric looks like. So that's why people fight for every 4th and 5th decimal point in the metric, and that's why techniques like crazy stacking and crazy multi-level ensembling are often employed at Kaggle, because gets that boost. But when it comes to the data itself, so real people prepared that data, and people can make mistakes. People export their own dirty data, and leakage can happen sometimes. Especially, it can happen sometimes when they try to meet certain requirements from Kaggle itself. So that when they try to anonymize their data, or when they try to provide a data set that's large enough for the leaderboard to be evaluated correctly. So what can happen? There are 4 or 5 different cases that I remember. So one of them, the competition organizers wanted to not expose information about particular customers or users, so they anonymized the user ID column. But actually, anonymizing customer ID, so I'm speaking about competitive machine learning right now, but it actually applies to real-life modeling as well, because simply because you anonymize or like remove the customer ID column does not necessarily mean a machine learning model cannot reconstruct or cannot de-anonymize this customer from other data. So if you have a particular purchase pattern in an online shop, or if you have a particular time you visit particular websites on the internet, so your telecom operator can actually use machine learning to de-anonymize this data even if they don't have customer IDs or user IDs. So simply removing the ID column does not necessarily mean your data is anonymized. So what people have done in this competition is they used other columns to actually find which rows in the data set belong to the same person. So it's often when you discover patterns like that in a competition, if you actually find out that different rows represent the same person, even though the competition organizers wanted to hide this fact from you, there's a lot of target leakage happening. Because if you can predict the target for a particular row, that means you can reconstruct this target for many other rows. Usually it happens in these competitions. It also happened in a very recent competition I participated in, Santander Value Prediction. So the setup of the competition was that you have a very anonymized data set, so like 4,000 columns and 4,000 rows with completely anonymized names, so it's completely like gibberish names. You cannot know what each of the columns mean, but what people found out during exploratory data analysis that this data set actually represents, so the goal of the competition was to predict the value of customer transactions. So a bank wants to expect how many near-term value they can expect from this particular customer, so many dollars they will bring to the income of the bank. And this is done by analyzing the history of client transactions and predicting the amount of customer transactions a few steps ahead. So what actually happened in this data set is that they have, people have discovered that actually what the data set was about, it contains a history of recent transactions by the customer, so about like maybe 40 recent transactions, and it was actually a time series problem. So we had to look at some number of recent transactions from the client and predict the value of transactions 2 steps ahead. And what the organizers have accidentally done is that they included in the data set overlapping different ranges from different customers. So for example, you can have your you are customer A, and you have your transaction history from June to January, and you have another row representing your transaction history like shifted a bit forward. So like you have June through January, and you have another row representing the same customer, but August to March. And if you have a range when you are given June through January, and you have to predict March, so like 2 steps ahead, 2 months ahead, but you already have another row that contains the exact value for your transactions in March. So people have actually reconstructed, like realigned these different time ranges for same customers, and actually like some rows completely leaked the target for, like more recent rows completely leaked the target for past rows, because you already have an answer lying somewhere in that table for this exact customer. So the competition pretty much reduced in the end to like reconstructing proper, like realigning proper sequences of transactions of customers, and like assembling leaks in the proper way. So you should not do this. If you have a time series problem, you should not have a training record where you have an answer for another row in this same data set. So this usually turns the competition into something completely different.
So how does this relate to real life situations where we don't have a competition? We exactly know where the time series starts and ends, and you don't have this problem.
Right. So I would say this particular example is not very relevant to building models in real life because you don't have to people to compete there and compete who builds the best model. But it's just like I mentioned before, like machine learning competitions usually provide very interesting types of leakage that you would not normally see when you build models in your own job, but an interesting and clever way people exploit the patterns in the data to reconstruct the target without actually having to build machine learning models. So sometimes the answer can be found in the data set itself rather than building a machine learning model to predict this answer. So for computational organizers, it's also, it sometimes happens that target can be contained in some side channel information or be available in the external data set. So maybe you released some of your data in the internet a while ago, and you launch a competition using a very similar data set. So users can find some of your data on the internet and use that to predict the target. Or an interesting example was the data competition a couple of years ago, when we had to predict whether a particular message, post is a sponsored ad or non-sponsored ad, and it actually was a very interesting leak in this competition. I believe they had to replace the data set or like relaunch the competition because of it. So the timestamp the data set was a collection of HTML files. So you were supposed to analyze the content of HTML files and make some predictions, like build a machine learning model that maybe analyzes the text or some particular patterns in the HTML file to make a prediction, whether it's a sponsored ad or a non-sponsored post. And where was the leakage? The leakage was in the timestamp of the HTML file. So the competition organizers thought that the participants would look at the content of the HTML file, but they looked at the timestamp of the HTML file. And the timestamp of the HTML file was strongly correlated with either the class being positive or the class being negative. So instead of looking into the content, the participants look at the metadata of the file and use the date of the creation of the file as a strong predictor for the target. So yeah, that's it sounds a bit ridiculous, but yeah, this just to give you a taste of what can happen sometimes in the competition. So you can accidentally leak your target, not necessarily through the content of your data set, but through side channels like metadata of your data or some external information. All right, so what can we do to actually reduce our chances of introducing target leakage into our data set? So what can be the prevention measures for target leakage? So unfortunately, this problem does not lend itself necessarily to easily to automated analysis. So there's no single like automatic silver bullet that would solve all the problems with target leakage on all possible stages of the data science project. But there are some recommendations I can give that will allow you to eliminate the majority of the cases of target leakage. So first of all, split away the holdout immediately and do not transform it in any way until you are ready for your final model evaluation. So when you have new data, set aside the holdout partition immediately and do not train any imputers, any scalars, any vectorizers, any transformers, any feature engineering tasks on it. So like immediately set it aside and do not use it until you're ready until you've selected your features, selected your model, and you're ready to calculate the final score of the model you are confident to deploy. So for these data collection and data preparation issues, make sure you have a data dictionary in place and that you understand that what each of your columns means and what each of the special values in the columns means. For example, you can have negative like minus 999, and you may not necessarily know what this means. So it's helpful to have a data dictionary in place to have complete confidence that you know what each of the columns in your data set means, whether it's not accidentally a transformation of the target, like target measured in imperial units rather than like inches rather than meters, or pounds rather than kilograms, or British pounds rather than US dollars, because it can happen, and the column names can be cryptic and not obvious at first. Yeah, it's also a useful thought experiment to try, like especially if we have quite a few columns, to try and answer the question: if we deploy this model, so we train our machine learning model in this particular set of columns, will I have this particular column in production? So try to imagine the actual scenario, so like when the predictive model is invoked and how a person who uses the model uses the prediction and adjust their behavior based on the prediction of your model. So try to imagine a real case when your model is already deployed into production and you request predictions from your model and how you are going to respond to these predictions. So, and for each column, I would advise to answer the question: will I have the value for this column in production? What kind of values can I receive? So that will help with cases like late payment reminder count, or number of surgeries our hospital already performed on this patient. So if we try to imagine, will we perform any surgeries on this patient at the time of admission, we will have an answer: no. It will always be 0, so any training data that has non-zero values is irrelevant. Yeah, so figure out preprocessing parameters strictly on the training subset and freeze the parameters, like freeze the mean and standard deviation of standard scalar, freeze the columns of TF-IDF vectorizer or whatnot, and figure out all of these parameters only on the training set and just freeze those parameters and transform any evaluation set you will have later. Right, so treat feature selection, model tuning, and model selection as separate quote-unquote machine learning models that have to be individually validated. And yeah, with group partitioning, with time series forecasting, with cold start problems, make sure that whatever you deploy your model for actually represents your validation framework. So this is especially valuable in competitive machine learning, like if you participate in competitions, because the absolutely best thing you can do in a machine learning competition is have your validation scores change synchronously with your leaderboard score. So if your validation framework represents your leaderboard progress, that's a very good validation to have. That's a very good situation to have. So if you have to forecast time series into the future, make sure your validation flows represent that problem. Or if you have to predict an unseen group of things, make sure your validation represents that cold start problem. And one thing that can also help is when you trained a predictive model and you computed the score, check feature importances. So either something that can be natively reported by models like linear regression or tree-based models. Actually, just look at the feature importance chart, or you can use something model agnostic like permutation importance to explain the predictions of the model and to explain the feature importance for the model. And just try to look at the top features that the feature importance score reports, and try answering the question: does this make sense from the domain point of view? And if it doesn't, it probably means you need to eliminate that feature altogether, and it introduces target leakage. So I have this example in the code here. If you look at the first notebook. So I took, as an example, I took a data set. It's openly available data. It's a semi-annual salary survey for Ukrainian software engineers. I tried to simulate that exact issue I showed before. So we have this bunch of data. We have city the person lives in, company size, company types, experience they have, English level, and so on. And a subtle thing here that we are trying to predict annual income in US dollars, but we have also monthly salary in Ukrainian currency. And when we try to build this model, so we encode our ordinals, our categoricals, our numerics, filter out the features that we need, and we then try to predict the salary and try to calculate the explained variance of the regression model. And we see that it almost perfectly explains the variance in each of the cross-validation folds. So we set up a 5-fold CV and try to estimate, assess the model performance on out-of-sample data, and we see that it almost perfectly predicts out-of-sample data. So usually if the scores look too good to be true, that probably means you introduced leakage. Either in group partitioning, you should have done group partitioning, or you have some issues with data collection or with feature engineering. So let's see what went wrong here. So I used XGBoost in this particular case, and XGBoost can natively report feature importances. So like it uses the statistics of which features were used in tree splits to come up with an estimate of how important this feature was in general for the whole data set. So let's plot the importance as reported by XGBoost. And we see that by far the most important features turned out to be monthly salary in Ukrainian currency. And if we try to validate this using the domain expertise, education makes sense, current workplace experience probably makes sense, English level probably makes sense, but they are just shadowed by this monthly salary UA. And if we try to imagine, will we have this model, this feature at prediction time? We absolutely would not, because the person is not yet employed at that particular workplace, and they will not have a monthly salary assigned to them. So we should just eliminate this feature. And after eliminating this feature, we try to calculate these out-of-sample scores again, and we see that explaining variables looks a lot more reasonable. So we explain about 70% of the variance in the salaries. We don't have many features to explain that. And if we plot the importances, it looks a lot more interesting right now, a lot more reasonable. So seniority of the person, whether they are junior, middle, or senior, total work experience, how many years they work in this profession, company type. So company type startup, I would believe that's an important feature, because startups can either pay low and give you equity, or they can pay you above the market to attract people from other big companies. So I would believe that whether the company is a startup is a good predictor for expected salary in Ukrainian market. So yeah, total work experience, English level is very important, education, and company type. Yeah, it now makes sense. And I also tried to reproduce this example on a toy data set, on a Titanic data set. I will probably update it if I come across a better public data set, maybe something time aware. But I tried to reproduce the issue of standard scaling the entire data set versus standard scaling only the training part. So I used a well-known Titanic data set, so we predict whether we will survive on Titanic or not. And yeah, so what I do is I apply mean imputation and standard scaling on the entire data set. So we have a lot of records where we don't know the person's age, so we just impute those with the mean and create an indicator variable. It's often useful to create a variable like this. So before imputing, we actually create a variable that says, was this value missing or not, before we imputed it. So we imputed it, we created an indicator variable, then we imputed it with mean imputation. So mean imputation says the mean age across the entire data set is 29.7 years, right? And we have the standard scalar results from the entire data set. So we train our classification model. I use k nearest neighbors because it's quite sensitive to scale and distance. It will show good insights here. So we calculated log loss on a test set. We calculated area under ROC curve. And then we try the same experiment, but with proper standard scaling and proper mean imputation right now. So instead of scaling and imputing the entire data set, we now split first. So we repeat the same data reading and feature encoding process. Then we partition first. So we first allocate our training and test sets. Then, only then, we apply mean imputation and standard scaling, but only on the training set. So we fit transform the train set, but only transform the test set. So we use fit transform here, and you see what happens. So if we used it on the entire data set, our estimate of the mean was 29.7. But if we only mean impute the training part, we have 28.9, which is a different summary statistic. And same thing happened with our standard scalar. So that was an example of leaking some information from the test set into the standard scalar and mean imputer. And if we try to repeat the same model, so same model with same random seeds, same parameters, same training and test folds, we have a different log loss, we have different AUC. And if we try to take a difference of what we had before and what we had after, we see that after applying proper mean imputation and proper standard scaling, we got a worse log loss and we got a worse AUC. So of course, like these techniques, they will make your development scores worse, but it's all for good because you will have a better estimate on you will have fewer surprises when you deploy your model into production. So it's kind of good to apply proper practices and get worse scores as a result because you won't have any significant surprises when you actually deploy these models into production. It's better to know the issues with your model before you deploy it than realizing it afterwards. Right. Yes?
I'm quite surprised by seeing that surprisingly large difference in the mean. How different in the log loss of the AUC?
Yeah,
Do you have any intuition about
Yeah, I admit I might have exaggerated this situation a bit because the data set is pretty small. It's a bit less than 1,000 samples. So I specifically used a model that is very sensitive to scale and to distance. So I used k nearest neighbors with number of neighbors 3. So it will have quite a lot of variance and a lot of sensitivity to changes in scale. So I just wanted to have a publicly available and well-known data set. And at the same time, I wanted to illustrate this effect of properly applying feature preprocessing having an impact of the scores. So it's only like a difference in third decimal point in the AUC, but still for competitions is going to be very significant. And for large corporations, it's also very significant. So we've seen cases like when a bank had an improvement of in 1% of accuracy, and it's translated to hundreds of millions of dollars. So applying small good practices in the project pipeline can bring quite significant dollar value. So this shouldn't be ignored. Right, so this is pretty much what I wanted to show you today. And yeah, if you have any questions, you can either ask me offline, or I'll be here for the entire conferences. Feel free to ping me whenever you see me, or message me in the app or on LinkedIn or whatever. So I'll be happy to answer all your questions if you have any left. Yes.
I was thinking, so you have this example of, I think, what was it, credit default, where reminders were sent, like these features that vary in the cost count. Oh, okay. Okay, so we had this example of credit defaults that were being sort of, where one feature was the number of reminders sent, and which is a feature that, so these late payment reminders,
Yep.
So which is a time varying feature. So I was wondering, still this is useful information to some degree. Would it, for example, make sense to use periods that have ended, save the data that we have so far, essentially, for completed periods, and then fill the rest with NAs?
Oh, it's a very good point. So if I understood your questions correctly, so I wouldn't say that this is a bad thing in general to have a case like this. So it all depends on how the deployed model will be used. So for example, you might not necessarily use the predictive model on the stage where the person is not yet our bank's client. But for example, we might grant the loan to a client and then reassess after a month, after 2 months, after 3 months. So in this case, it's okay to use later snapshots if we train the model to specifically predict the loan defaults after the person is already our client. So it all depends, like whether the thing is a leakage or not. It only depends on how the model will be used in a workflow when it's deployed. So if we strictly expect the client to be yet unknown to us and not be a client of our bank yet, not have a history of reminders yet, then it's leakage. If we want to train a model for further stages, like detecting early risk when we already gave loan to a client, then it's okay to have other snapshots and train other models on mutated stuff. So yeah, the point I was making is just the snapshot of the data you use for training must match the real life workflow you will use this model. Yeah, but that's a very good question.
Okay, thank you.
You going to share the presentation with it?
Yes, so the presentation and the code examples are available here. So I have a PDF copy of the presentation. in this repository. So yeah, I think recording and the slides and the materials will be published in the conference materials. I just don't know yet how it exactly it will look and how it will be sent out. But yeah, as far as I know, this session is recorded, so I will also provide the materials to the conference organizer. But in any case, you can clone this repository right now and have all the information available to you. Yeah. All right, so I take it we don't have any other questions. Oleg, thanks a lot for attending my talk. I really appreciate such a good crowd. And yeah, have fun with the rest of the conference and catch me anytime if you have any questions.
Thank you again to our speaker for the great presentation. I just want to remind you the invitation about the meetup that we have on the Mansi room. It starts at 6 p.m. Thank you.
And please rate the talk in the app. I would be very interested to know what I can do better. Yeah.